Jsem tam? Jo? To funguje nějak.
Jsi na tom místě?
Jo. So, English. So last time we introduced a representation round. And we give a citation to Haberman, where it is described with the proof and citations. And today we shall briefly introduce the complexes. The complex. So the complex will be introduced as associated complex. So first we have such a map, which is a homomorphism of Lie groups. And we can therefore consider such a space, not only space, but a space equipped with representation. So consider this. I will write it maybe what it means. And this lambda I denotes also the dual to the representation. So to be precise, I will use this. So how to write it? So this is formula for the case when alpha is the I form. More general definition is that it is extended by linearity. And the dual representation is just given by the formula this is the usual prescription for dual representation. G is from MP. So now what is this rho I on G acts by I wrote it already. The tensor product representation. So you can either induce this representation to any principal and bundle for the group MP and obtain a sequence of spaces. Yeah. So we do it. So representation is here. And now we suppose that we have such a structure on the manifold. Sure, I should be more precise. Should write here also the dual. It doesn't. Actually, the representation of on B dual is equivalent to the representation of B by the identification by omega 0. So this space, what is this? What is it? It is somehow a replacement for the structure of MP by this vector space. So formally, it is a Cartesian product modeled by a relation of this type. So we identify two elements if they satisfy this relation, and one can think of it as these elements as reference arcs on the manifold. They are actually in P, not in Q, which is the space of symplectic repair. And we identify them if they are connected by such an affection of necessarily an element of the symplectic group. And the vector parts, these W's, are related by the representation. So this is a definition of associated bundle for an induced bundle. So it's typically the space of vectors or the coordinates of the vectors. Yes. So we change bases and change coordinates appropriately. So the vector doesn't change. This is one of the possible explanations for it. So the fiber now. It's isomorphic to this space. This can be seen easily. This row lambda is merged into GL and row I as well into GL over L to L space. Okay, maybe when you see it for the first time, you might be surprised. I made a mistake here. The action is supposed to be from the right. Does it make sense? Lambda G0 is in the SP, and it acts from the right on the repairs. So it's supposed to be from the right. Okay. So here something like forms tensored by this L2 functions. So twisted by L2 functions. So this space can be named as symplectic spinor. This is the name for L2 in this theories. Symplectic spinor value I forms. Exterior I forms. So then we know that we have there is a symplectic connection. There are plenty of them. By the result of Tonnerre. And there is also a procedure how to lift symplectic connections to the symplectic repair bundle and then further to lift it to this bundle P. FM connection, then principal bundle connection, transfer principal bundle connection, and then we have a map. S, but S stands for, it's an abbreviation for the space L2M. So this procedure is prescribed. Do you know some convenient book for these associated connections, Peter? How to form associated connections. Kolář Michal Slovák. For example, Kolář Michal Slovák. Natural operations. In differential geometry. There is another very general approach, or Haberman, where it is described as well. So this induced connection is might be called symplectic spinor covariant derivative. So as a map, it takes a vector field, a section of the symplectic spinor bundle, and it gives again a section of the symplectic spinor bundle, where the symplectic spinor bundle S is just E0. It's better to write it in this way. So up to now everything is understandable. Here the non-trivial construction is the one of the associated bundle. So must prove that there are smooth atlases and so on. There are of course problems with that in the infinite dimensional case. So strictly speaking, one should take only smooth functions inside L2L and then associate these functions whether the atlases are really smooth. But I don't speak about this analytical issue already. This curly SL denotes the Schwarz space of rapidly decreasing functions on L. So this shall be associated in order the transition maps are smooth, which is dense in L2. So this finally is the conclusion. And now, how can we form complex? Maybe in order it is not so wild, let us go back to the Dirac complex. Yeah, so the Dirac as an example. So we start with a smooth manifold M, and as you know, we produce exterior forms. And on it we have a Dirac map. Given by the formula, block of formulas. For example, these formulas. So what are exterior I-forms? There are sections of the i's exterior tangent bundle, the i's exterior cover of the tangent bundle.
Cotangent bundle.
Or cotangent. Cotangent bundle.
Yes.
We would like to see this cotangent bundle in the context of what we said previously. It means as an to see it as an associated bundle. So we can form a bundle of all frames on M in any point. And then we can multiply it by the vector space, which is the ith exterior cover of V, where V is now a fixed space, vector space Rn, where n is the dimension of the manifold. So it is it is somehow a model of the manifold. So we can do this. And then we can mod out by the relation similar to the previous one, only with different representations. Where sigma is the representation of GLD on the ice exterior over. So I identified too much. I will check on specific first. Okay. So it is a representation, the tautological one. And similarly for alpha from the exterior forward, for wedges in each couples, in each coordinate. So this is classical construction of a tangent bundle, seen as an associated bundle. So this is how we can view the complex of Dirac. So maybe you know that the representation of GL on the exterior forms are irreducible. So this is a fact, simple fact. They are almost irreducible also for the orthogonal group, except possibly in the middle dimension. If n is 2m, then lambda m is decomposable with respect to SO, with respect to SO. The basic fact is this in the case of the round. A further example negative Dirac complex tensored by the tangent function. We don't actually know how to differentiate. So let us suppose that M is a Riemann manifold, so G Riemannian metric. As usual. And normal G be the Levicevita collection. So I will write it. In this case, we can define the twisted Dirac differential. By this non-Elegant formula, where epsilon I is dual to EI, and EI is a local basis of EM. In any point, we choose an open set in M and take a local basis over U. So in each point N from M, E, I in point N is a basis, smoothly. This is possible. You can take, of course, coordinate vector fields of this on U by the definition of manifold. But in general, we don't have the property as in the case of the RAM. That composing I plus first and I D tilde would give 0. From this defining formula, one can actually compute not so difficult, in a not a difficult way, straightforwardly, that composing these DIs correspond to the action of the curvature of the Levi-Civita collection. So actually the curvature acting not on vector fields but on duals and on exterior power. So this is somehow easy. So, we can reformulate it. The curvature is actually the obstruction for these operators to form a complex. So theorem di tilde is chain complex if the curvature is zero. Which on the other hand makes the situation not so interesting for differential geometry, because typically one is interested in curved manifolds, in manifolds which have some curvature. So this actually is not so interesting, but in symplectic geometry we have a big freedom of choosing of symplectic connection. The connections are non-unique. They are formed by the space, as mentioned already twice, sections of the symmetric over the cotangent one. Or if another example, if M is a complex manifold, then we have then we have operators D and D bar. Okay, but we have also PQ, let's say PQ or IJ, let's say IJ, differential force. I will speak about it in a local situation. Yes. I will take PQ forms. I would have II and so on. Unreadable. This is I. So we have such forms on a complex manifold given by the complex structure J, which induces these barred coordinates. V and V bar. Given by the similar formula. This I is this. So these are these Bettinger or Dolbot operators. Aha, so this may be dz bar. dz bar is, I don't know, so first it is dz, 1/2 of such derivatives of dxi and ddy. And dz I bar is just this. So these operators form also complexes. We can denote them when they act on I-forms by di. So that's actually this. We have also this formula. Which makes the space of PQ forms a bicomplex. EPQ denotes the space of P times holomorphic and Q times anti-holomorphic forms. This definition doesn't depend on the local coordinates here, which can be surely proved this way. The Deran the Dolbot without bar rises the holomorphic degree, and to this bar rises the anti-holomorphic degree. So actually let's take the PQ goes into this space. I mean, PQ goes to P plus 1Q. simply here. So there is also no curvature seemingly, but if we start with a almost complex manifold, then there will be something like an obstruction for these to be a complex, a chain complex. And this is the Nijinhu's tensor. I don't know if you know it. The Nijinhu's tensor is defined in a way that an almost complex manifold is complex, typically induced by a holomorphic structure, if and only if the Nijinhu's tensor is zero. And if the tensor is zero, then the just opposition, the composition of these D's and D bars is zero. So, what would you expect? We would like to relate this complex to Dirac and to the complex twisting by Tm, as in the previous cases.
So not to be confusing, so you should also write to epsilon and dE bar if you integrate the thing like by complex.
Which epsilon?
The last of one line. The last of one, this one to the left.
Yeah,
yes.
gamma.
Not only gamma, not only that. Okay, that's fine. But also D bar in that case is bicomplex.
Yeah, okay.
So D and D bar are two sort of differentials. Which means that something like collection bicomplex.
Yeah, how to see these bundles as associated bundles. EPQ is, and this is not so easy. Sure. So we can form these bundles if Em complexified, meaning Tm in each point is complexified as a vector space, decomposes into two complex vector spaces, two vector spaces, with respect to the action of the complex structure. So this corresponds to the I and to the minus i's eigenvalue j. From this point of view, j is given by in coordinates only. must say that I speak now only about an example of a complex structure. I will not. It is not easy now to introduce complex structure and go too much into the origins. So. It was here on the rails. There's a complex structure on CL. Okay, maybe we can get to that further next week. Because complex manifold is usually given, so you take a differentiable manifold, and if you can form the atlas in the manifold such that the transition functions are holomorphic maps from Cn into Cn, then the manifold is complex. Complex functions on Cn are defined as solutions of the Cauchy-Riemann operator in each coordinate and smooth. And okay, so it will be not surprising, not a miracle. Here on the Cn, you have such a map given by this matrix, and you can define this J on Cn, you can put it to the manifold, you can transplant it to the manifold if you have a complex atlas, homomorphic atlas. And if you start with a smooth manifold and a smooth map J from Tm to Tm, then so the smooth setting, if you have J, if you have a map J from Tm to Tm, such that J squared is minus identity, then M has a complex atlas. So it's induced by an, so it has a complex, it has an atlas whose transitions are holomorphic maps. This is the definition of complex manifold. If and only if the Nierenberg-Nuremberg tensor vanishes. So we are getting a bit to the foundations, but not as we would like to. So this, if we have this, then this is holomorphic or complex, if and only if some 2-1 tensor vanishes. And if we have a complex manifold, this J exists and is defined by this prescription transfer to the manifold. So, okay, these are very brief introductions into complex manifolds. Now we shall go back to this formula. P times holomorphic Q times anti-holomorphic forms on M. Can we view them as representations? Rho PQ will be a representation of what? Of the unitary group. On this space. Automorphisms. Where V is again the model space of the tangent space and point of the manifold of dimension 2n. Complex manifold must have even dimension. And one can form can decompose it. I mean, the tensor product R2n times C can be decomposed into two vector spaces with respect to the eigenvalues for G0. So we have some more repetitive structure of the lecture. It can be proved that they have the same dimension whenever J0 is such that J0 square is -1. And one can consider such a representation, obviously. In an obvious way. Rho PQ G of the form just G on alpha times G on beta, where no G alpha is given by the same formula. I don't write the lambda. There is no lambda. And these spaces, what does that move them? FPQ are irreducible for the representations of UN irreducible. So you can be motivated by these examples to construct by these three examples. Deram, listed Deram by tangent, and this complex manifold tangent bundle complex to get a further example in symplectic geometry. We have an attempt to do that. He spoke about the possible Laplace, that it doesn't exist in the symplectic case, because I mean, what could be a Laplace operator, the composition of these of the connections would be of order 0, wouldn't be second order operators. The Laplace is said to be non-existing in the symplectic complex somehow. So these achievements regarding to find complex and symplectic manifolds are usually attributed, or they were found by Lichnerovich and Brilinsky. So if M omega is symplectic, one can look at Lichnerovich and Brilinsky. So there is also a possibility of defining a parallel analogy of each star. And these attempts also led to something which is called formality. Formality of homology groups. And Mathieu also. So this is just a remark that we will not follow actually, this approach. I don't know actually how it is popular now, or what is successful in the context of quantization and other procedures. If somebody knows it, it would be a good topic for a seminar we've developed. So we will do something similar in the context of manifolds with metaplectic structure and symplectic connection. So we have representations of the metaplectic group. We associate them to the I-forms with various symplectic spinors. And this is the metaplectic representation introduced last week. And we can also then, okay, what to do with the connection. Connection induce these spoke about covariant derivative. And the covariant derivative, symplectic spinor collection, doesn't compose to zero in general, but it composes to the action of the symplectic curvature. The symplectic curvature is known to have only two independent components. Yeah? So it composes into the Weil and symplectic Ricci part. So this was only mentioned. It's similar to the Riemannian geometry, but there is no scalar curvature. This is the difference to the previous case. There is no scalar curvature. So this is a referred result of Weissmann, which I recall from last time. So it is different from the cases actually introduced. Yeah. So this space is not irreducible. So these spaces are not irreducible. And they decompose into direct sum of submodules if I is less or equal to n. If I is bigger than n, there is a similar description. Oh, but actually, this is given by this isomorphism. Now the dimension of the manifold is 2n. So it is not similar to the Dolbot situation, it is not similar to the Deram. It might be seen to be similar to the twisted Deram by tangent bundle. Okay, what we have, let us draw a picture. How this decomposition can be visualized for six-dimensional manifolds. So we have zero forms. This values in symplectic spinor. This is just the space of symplectic spinors. Then we have forms with values, one forms with values in symplectic spinors. And this decomposes into two submodules, which further decomposes, but we will not speak about that yet. Then we have two forms. They decomposes in this way, three forms. They decomposes in this way. And the forms of degree bigger than the half of the dimension of the manifold decompose corresponding to it. So now I will mention the irreducibility of Eij. Eij decomposes into a direct sum of just of two representations which are irreducible. The metaplectic representation itself decomposes also into sum of two irreducible representations, as we spoke last time. So these irreducible decompositions can be proved using formulas of Bernstein. So the result is Eij plus minus R irreducible. And P2 and R modulus. There are similar formulas to the clinic formulas, which goes back to Hermann Weyl, but for the case of infinite dimensional representation of X. By Weyl, they were achieved for tensor product of finite dimensional representations. There are generalizations for infinite dimensional cases. Actually, Bernstein uses that, but good reference is Janssen. It's too much representation. Karsten Janssen. So maybe what can be done with this decomposition? Since it is a decomposition with respect to the structure group, it leads to associated bundles. So we can form again associated bundles. Rho PQ, which I define. Rho PQ is just representation. Restriction. Since EP EPQ is in the P forms by so this doesn't correspond to the complex geometry notation. Usually in complex geometry EPQ means a form of degree P plus Q, maybe denoted by P. This is my conventional choice. Rho pi was introduced at the beginning. So one has set bundles. Now to have a complex, we must also define an operator induced by the connection in this case. We don't have the property of the induced connection to rise the first or second index, P and Q in this case. We use this property. There are further symmetries which can be found for this operator D. But maybe I will just formulate the main result and we can naturally stop because I think there are also, from my point of view, many informations maybe so, today which didn't prove almost anything. So I will just mention the theorem. So if m omega nabla is a Ferrosov manifold, that admits a metaplectic structure. And such that whose curvature, whose not the whole curvature, it's the whole point, whose line curvature, whose line curvature vanish. M omega Ferrosov is metaplectic structure. If m, better to say, if m omega nabla is a Ferrosov manifold admitting the metaplectic structure whose curvature vanishes from the connection here, then then dp q forms any Q. So is it understandable? Probably yes. Oh, so this is a theorem, so it takes some time to prove it. We stop with this yet, yeah, so it's not a good point for a lecture. So next time we can actually finish these lectures by saying more words about this.
So what are examples of symplectic manifolds with trivial Wales or trivial symplectic Wales tensor?
There are plenty.
Okay, so at least so what they are. So even dimensional spheres, for example.
Yes. Open manifolds typically. So examples, whether this structure exists. Many people started to ask last times whether the manifolds exist. So there was a big question in 90s, and there were found locally open manifolds in R2N admits plenty of connections of the so-called symplectic Ricci type. This is the same as wide curvature vanishes. Synonyms. So these consider existence subsets of R2N. This is connected to so-called preferred symplectic Ricci type connections of Cahen, Good, Schwackhofer. So, Good, Lorenz Schwackhofer, and Bourgeois, Frederick Bourgeois also. And there are global questions. There are global questions, like really spheres, or I wouldn't say sphere, I would say really CP. I was too generous. CPN. CPN is Kubinin studiometry. And standard complex structure inducing omega, inducing symplectic form by the 2 out of 3 property. Then there are for sure CN and tori. And they are coverings. So not so many, but nice examples. In general, actually, it can be proved that any complex manifold with bisectional holomorphic curvature 0 apply. No bisection, holomorphic, it is called just holomorphic sectional. Sectional curvature. Bisectional curvature is something different. Constant. You know, they need to be even zero constant. So any space with such a curvature. There are also non-complex examples. Kodaira-Thurston shall admit it. Kodaira-Thurston manifold. This is quite famous manifold, which is symplectic but not complex.
So for example, if we have CPN and there is a Fedosov connection for which this manifold has trivial symplectic veil component of the curvature tensor. So if you change this connection infinitesimal in some way by that symmetric three tensor, then what? So it cannot have trivial symplectic veil tensor.
Probably.
So it doesn't have or can have sometimes or depends on that symmetric three four.
I haven't looked at this question, which is quite interesting.
No, I don't know. I'm asking because I don't know whether this.
It can have torsion, and it still can be.
Well, I'm asking about this property. So I don't know how much exceptional this property is. So because the space of symmetric three tensors is big, large. So what? So is it quite exceptional that to have for the choices of symmetric three tensor?
I don't think it is.
That the symplectic veil part of the curvature is really trivial.
From the point of view of what? From the point of view of the curvature.
Yes,
from the point of view of a curvature, if this is fixed, then the while to be zero is, represents much more conditions than reaching to be zero.
Okay, so is it exceptional? So if I have one Fedosov connection and I'm changing it by adding symmetric three tensor, so I'm asking whether this is exceptional property, the property that it's symplectic veil component.
I wanted to study this question with Petr Franek many years ago, and then we stopped doing it.
So what's the intuition? So should it be exceptional or shouldn't be exceptional?
It's not. I don't know.
You don't know. Okay, so that's the answer.
So okay, this I wanted to motivate you to find further possible complexes, and I didn't give a machinery, but almost a machinery for that. Introducing the Delam, Dombov, and also this in between these complexes in between some manifolds with some preferred structure. So that's all. Thank you for your attention.
So what about the next week? So I can talk. I'm able to find some topic, but it also depends on you.